The notion that Japanese aircraft were somehow inferior or paper-like gained particular prominence following several key engagements in the Pacific War. American pilots' first major encounters with Japanese naval aviation occurred during the attack on Pearl Harbor on December 7, 1941, and subsequently during the battles of Coral Sea, May 1942, and Midway, June 1942. However, it was during the campaigns in the Solomon Islands, particularly around Guadalcanal from August 1942 onward, that American fighter pilots began accumulating sustained combat experience against Japanese aircraft. Initially, American forces were shocked by the performance characteristics of Japanese fighters, particularly the Mitsubishi A6M0. The Zero demonstrated remarkable maneuverability, range, and climb rate that exceeded American expectations. This initial superiority lasted through the early months of 1942, during which Japanese aviation dominated the skies over much of the Pacific. The revelation about Japanese aircraft vulnerability came not from a single dramatic battle, but through accumulated combat experience as American pilots developed tactics to exploit specific weaknesses in Japanese aircraft design. The Mitsubishi A6M0 Engineering Philosophy and Design Priorities. To understand the paper airplane characterization, one must examine the design philosophy behind Japan's most iconic fighter aircraft, the Mitsubishi A6M0. Designed by Jiro Horikoshi and entering service in 1940, the Zero represented a deliberate set of engineering trade-offs that prioritized certain performance characteristics over others. The Zero specifications were extraordinary for its time. It possessed a maximum speed of approximately 534 kilometers per hour, a range exceeding 3,000 kilometers with external tanks, and a service ceiling of 10,000 meters. Its armament consisted of two 20mm cannons and two 7.7mm machine guns. Most remarkably, it had a wing loading of only 107 kilograms per square meter, contributing to exceptional maneuverability that allowed it to outturn virtually any Allied fighter in 1941 to 1942. These impressive capabilities came at a deliberate cost: armor protection and structural durability. The Zero achieved its performance through extreme weight reduction. The airframe utilized extra super duralumin (ESD), an aluminum alloy developed by Sumitomo Metal Industries. This material offered excellent strength-to-weight ratios, but required careful handling during manufacturing. More significantly, the Zero initially lacked pilot armor, self-sealing fuel tanks, and heavy structural reinforcement. The aircraft's empty weight was approximately 1,680 kilograms, remarkably light for a fighter of its capabilities. This design philosophy reflected several factors specific to Japanese naval aviation doctrine. Japanese carrier-based aircraft required exceptional range to compensate for the Imperial Japanese Navy's numerical inferiority in carriers compared to potential adversaries. The doctrine emphasized offensive operations and achieving air superiority through superior pilot skill and aircraft maneuverability rather than through aircraft survivability. Additionally, Japan's limited industrial capacity and access to strategic materials, particularly high-grade aluminum and aviation fuel, necessitated lightweight designs that maximize performance from limited resources. American tactical adaptations and the discovery of vulnerability. American pilots' discovery of Japanese aircraft vulnerability emerged through hard-won tactical evolution. In early 1942, American fighters attempting to dogfight Zeros using traditional turning combat suffered devastating losses. The solution came through tactical innovation rather than technological superiority. The breakthrough came with the adoption of boom and zoom tactics, particularly championed by pilots like Major John L. Smith and Captain Marion Carl of the United States Marine Corps during the Guadalcanal campaign. flying Grumman F-4F Wildcats, which were inferior to the Zero in maneuverability and speed. American pilots developed tactics exploiting their aircraft's advantages: superior diving speed, structural strength, and firepower. The tactic was simple but effective. Approach from altitude, dive at high speed to attack, and immediately climb away before the Zero could respond. This approach prevented Japanese pilots from utilizing their maneuverability advantage while exploiting the structural limitations of Japanese aircraft. When American pilots achieved successful gunnery passes, they observed that Japanese aircraft often caught fire quickly or suffered catastrophic structural failures. This vulnerability became even more apparent with the introduction of the Chance Vought F-4U Corsair and Grumman F-6F Hellcat in 1943. These aircraft combined superior speed, firepower, and structural strength. The Hellcat, in particular, proved devastating against Japanese aircraft. Armed with 6.50 caliber machine guns delivering approximately 4,800 rounds per minute collectively, the Hellcat could inflict massive damage in brief firing passes. Japanese aircraft, lacking armor protection and self-sealing fuel tanks, proved extremely vulnerable to this concentrated firepower. The reality of Japanese aircraft construction. The characterization of Japanese aircraft as paper requires careful examination against the actual construction methods and materials employed. Japanese aircraft were not literally constructed from paper, nor were they shoddily built. Rather, they represented a sophisticated engineering approach that made different trade-offs than American designs. Japanese aircraft manufacturers employed several advanced construction techniques. The Zero's fuselage utilized a semi-monocoque design with stringers and formers covered by stressed aluminum skin. This construction method was entirely conventional by international standards and similar to contemporary American and European designs. The wing structure employed two main spars with ribs and stressed skin, again a standard approach. Where Japanese construction differed significantly was in thickness of materials and inclusion of protective features. American fighters like the F-6F Hellcat incorporated armor plate protecting the pilot from rear attacks, typically 6 to 8 millimeters steel behind the cockpit and 38 millimeters bulletproof glass windscreens. The Hellcat also featured self-sealing fuel tanks developed by the United States Rubber Company, which automatically sealed bullet holes through a chemical reaction when fuel contacted the tank's inner lining. The Zero Model 21, the most common variant in 1942 to 1943, initially lacked both features entirely. Later variants, Model 32 and beyond, incorporated some protective measures, including limited armor plate and partially self-sealing tanks. But these additions degraded the aircraft's performance and handling characteristics. The addition of approximately 90 kilograms of armor and protective equipment reduced the Zero's speed, climb rate, and maneuverability, the very characteristics that made it formidable. The structural strength differences were equally significant. American naval fighters were designed to withstand the stresses of carrier operations, particularly the violent deceleration during arrested landings. This required robust airframe construction. The F-6F Hellcat could safely dive at speeds exceeding 880 kilometers per hour, while the Zero's maximum safe diving speed was approximately 660 kilometers per hour. Exceeding this limitation could result in structural failure, particularly of the ailerons and wings. Comparative analysis: Japanese versus American design philosophy. Understanding the paper airplane perception requires examining the fundamentally different design philosophies underlying Japanese and American aircraft development. These differences reflected not just engineering decisions, but broader industrial, economic, and strategic contexts. American aircraft design emphasized survivability, firepower, and pilot protection. This approach was feasible due to several advantages. The United States possessed virtually unlimited industrial capacity, abundant strategic materials, including aluminum and high-octane aviation fuel, and sufficient carriers to operate shorter-range aircraft. American doctrine increasingly emphasized protecting trained pilots as irreplaceable assets, recognizing that a pilot who survived being shot down could return to combat with enhanced experience. Japanese design emphasized performance, range, and offensive capability while accepting reduced survivability. This reflected Japan's strategic constraints, limited industrial capacity, restricted access to strategic materials, fewer carriers requiring longer-range aircraft, and a cultural tradition that placed less emphasis on individual survival compared to mission accomplishment. These different philosophies produced measurably different outcomes. A Hellcat pilot hit by Japanese fire had reasonable survival prospects. Armor might stop or deflect bullets. Self-sealing tanks might prevent fire, and a robust airframe might survive damage sufficient to return to the carrier. A Zero pilot in the same situation faced much grimmer prospects. Without armor, any bullet reaching the cockpit threatened fatal injury. Without self-sealing tanks, fuel leaks frequently cause catastrophic fires. The lightweight structure, while agile, offered minimal protection. Statistical evidence supports this analysis. American pilot survival rates in the Pacific improved dramatically as newer aircraft entered service. In the Guadalcanal campaign, August 1942 to February 1943, American pilots flying F-4F Wildcats achieved approximately a 1-to-1 kill ratio against Zeros. By mid-1943, pilots flying F-6F Hellcats achieved kill ratios approaching 19-to-1 against Japanese aircraft. While improved tactics contributed significantly, the structural advantages of American aircraft played a crucial role in pilot survival and return-to-combat rates. The Nakajima Ki, 43 Hayabusa, and Japanese Army aviation. While the Zero dominated discussions of Japanese naval aviation, the Imperial Japanese Army Air Force operated different aircraft with similar design characteristics. The Nakajima Ki, 43 Hayabusa, Allied code name Oscar, represented the Army's equivalent to the Zero, emphasizing extreme maneuverability and lightweight. The Ki 43 carried this philosophy even further than the Zero. Early models, Ki 43I, featured only two 7.7 mm machine guns, extraordinarily light armament for 1941 to 1942. The aircraft's empty weight was merely 1,580 kilograms, and its wing loading was even lower than the Zero's at approximately 95 kilograms per square meter. This gave the Hayabusa breathtaking maneuverability. It could complete a 360-degree turn in approximately 11 seconds, among the fastest turning rates of any fighter in World War II. American pilots encountering the Hayabusa in Burma, China, and later in the Philippines observed the same vulnerabilities as with the Zero. The aircraft lacked armor protection and self-sealing tanks. Its light armament meant that even when Hayabusa pilots achieved firing position, they often lacked the firepower to inflict decisive damage on American aircraft. Meanwhile, American fighters like the Curtiss P-40 Warhawk, Republic P-47 Thunderbolt, and North American P-51 Mustang could destroy a Hayabusa with relatively brief firing passes. The progression of Japanese Army fighters followed a similar pattern to naval aviation. Later models like the Ki 43-2 and Ki 43-3 incorporated slightly heavier armament, two 12.7 mm machine guns, some armor protection, and improved engines. However, these additions compromised the aircraft's primary advantage, maneuverability, while still leaving it inadequately protected by Allied standards. The later war period Desperation and deterioration. As the Pacific War progressed, the quality gap between Japanese and American aircraft widened significantly. This deterioration stemmed from multiple factors beyond initial design philosophy. American industrial production accelerated dramatically, introducing superior aircraft like the P-38 Lightning, F-4U Corsair, and eventually the P-51 Mustang to Pacific operations. These aircraft combined the survivability features of earlier American designs with performance characteristics that matched or exceeded Japanese fighters in all areas. Simultaneously, Japanese aircraft production faced mounting difficulties. Strategic bombing, particularly by Boeing B-29 Super Fortresses from late 1944 onward, disrupted Japanese industry. The destruction of shipping by American submarines severed access to raw materials from occupied territories. Quality control deteriorated as experienced workers were conscripted or killed, replaced by increasingly unskilled labor, including students and conscripted civilians. By 1945, Japanese aircraft quality had genuinely deteriorated to levels approaching the paper airplane characterization. Late-war Japanese fighters sometimes featured wooden components substituting for aluminum, poorly fitted parts, inferior materials, and shoddy construction. Paint was often omitted to save materials and weight. More critically, pilot training had collapsed. In 1941 to 1942, Japanese pilots averaged 500 to 700 hours of flight training before combat assignment. By 1945, replacement pilots might have as little as 40 to 50 hours total flight time. This combination, inferior aircraft flown by inadequately trained pilots against numerically superior and technologically advanced American forces, produced catastrophic results. American pilots reported encounters where Japanese aircraft seemed to disintegrate under fire or fall apart during maneuvers. While this reflected genuine deterioration in construction quality, it also represented the cumulative effect of material shortages, industrial disruption, and collapsed training programs rather than inherent design flaws. The kamikaze campaign and material realities. The Japanese kamikaze campaign, beginning in October 1944, provides perhaps the most dramatic evidence of how material realities influenced Japanese aviation strategy. The decision to employ suicide tactics reflected multiple factors: the catastrophic attrition of experienced pilots, the impossibility of matching American material superiority through conventional means, and cultural factors specific to Japanese military tradition. From a material perspective, kamikaze tactics represented a recognition that Japanese aircraft could not survive sustained combat against American fighters and anti-aircraft defenses. Converting the aircraft itself into a weapon eliminated concerns about pilot protection, aircraft survivability, and return fuel. Essentially, the suicide mission removed all the design constraints that had previously necessitated trade-offs between performance and protection. The aircraft employed for kamikaze missions illustrated the breadth of Japanese desperation. While some missions used frontline fighters like the Zero, many employed obsolete aircraft, trainers, or purpose-built suicide aircraft like the Yokosuka MXY-7 Oka, a rocket-powered flying bomb. The Oka carried a 1,200-kilogram warhead, but was essentially a piloted missile launched from a mother aircraft. Its construction was extremely simple, primarily wood and steel, because survivability and reusability were irrelevant. American pilots and sailors facing kamikaze attacks indeed observed that these aircraft often appeared flimsy or poorly constructed. This observation was accurate for late-war Japanese aircraft, but it reflected the collapse of Japanese industrial capacity and the desperation of employing unsuitable aircraft for suicide missions rather than inherent flaws in Japanese engineering capability demonstrated earlier in the war. materials science, and industrial capacity. A deeper examination of the paper airplane myth requires understanding the materials science underlying aircraft construction in World War II. Aircraft structural strength depends on the properties of materials used, the thickness and configuration of structural members, and overall design approach. Both Japanese and American aircraft primarily used aluminum alloys for airframe construction. However, significant differences existed in alloy composition, quality control, and structural approach. American manufacturers had access to high-quality aluminum alloys, including 2024 containing copper, magnesium, and manganese, and 7075 containing zinc, magnesium, and copper, both offering excellent strength-to-weight ratios. Production quality remained consistently high throughout the war as American industry operated largely without disruption. Japanese manufacturers utilized similar aluminum alloys, but faced persistent quality control challenges. Japan's limited domestic bauxite resources necessitated importing raw materials, primarily from occupied territories in Southeast Asia. As American submarines devastated Japanese merchant shipping, these supplies became increasingly uncertain. Manufacturers compensated by using thinner aluminum sheets, reducing structural redundancy, and increasingly substituting inferior materials. The difference manifested in measurable structural characteristics. An F-6F Hellcat wing might use 2 mm aluminum skin over the main structural elements, while a Zero wing might use 1.2 mm skin in comparable areas. This difference seems minor, but has significant implications for resistance to battle damage. A .50 caliber bullet penetrating aircraft skin creates a hole and shock wave that can propagate tears in thin material. Thicker material better contains damage, preventing catastrophic structural failure. Furthermore, American aircraft incorporated structural redundancy, multiple load paths, so that damage to one structural member did not immediately compromise overall integrity. Japanese aircraft, designed for minimum weight, often lacked such redundancy. Combat damage to a main spar or primary structural member could cause catastrophic failure in Japanese aircraft, where an American aircraft might remain controllable despite similar damage. Psychological and cultural dimensions. The paper airplane characterization also reflected psychological and cultural dimensions of the Pacific War that extended beyond pure engineering analysis. American wartime propaganda consistently portrayed Japanese technology and industry as inferior, imitative, and based on cheap, shoddy materials. This served multiple purposes: maintaining morale, encouraging industrial workers, and reinforcing racial stereotypes that characterized Japanese people as inherently inferior. Early war experiences contradicted this narrative. The Zero's superiority shocked American forces, as did the quality of Japanese optical equipment, torpedoes, and other military technology. The cognitive dissonance between propaganda claims and combat reality required resolution. As American pilots developed effective tactics and superior aircraft entered service, the narrative could be reconciled. Japanese aircraft appeared superior initially, but were actually fragile and poorly protected, made from inferior materials, reflecting overall Japanese industrial inadequacy. This interpretation, while containing elements of truth regarding design priorities, obscured the sophisticated engineering decisions underlying Japanese aircraft design. Japanese engineers made deliberate, rational choices based on their strategic situation, industrial capacity, and operational requirements. These choices proved increasingly disadvantageous as the war progressed and American material superiority became overwhelming. But they represented sophisticated engineering rather than incompetence or inferior industrial capacity. Cultural factors also influenced pilot accounts and perceptions. American pilots, observing Japanese aircraft burning or breaking apart under fire, interpreted this through cultural frameworks emphasizing American technological and industrial superiority. The alternative interpretation, that Japanese engineers made different trade-offs based on different strategic circumstances, required acknowledging the sophistication and rationality of enemy engineering, something difficult to accept during total war. Technical innovations and missed opportunities. Examining Japanese aviation technology reveals significant innovations alongside the vulnerabilities that generated the paper airplane perception. Japanese engineers developed several advanced technologies that influenced post-war aviation development. The Zero's enclosed cockpit with excellent visibility, the long-range capabilities achieved through extreme efficiency, and certain aspects of Japanese aerodynamic design were genuinely innovative. Japanese engineers also developed advanced aircraft designs that never entered mass production due to industrial constraints and strategic circumstances. The Kawanishi N-1K J Shidenkai, entering service in 1944, incorporated many lessons from earlier aircraft. It featured armor protection, self-sealing tanks, heavy armament, 4 20mm cannons, and improved structural strength while maintaining good maneuverability. In the hands of experienced pilots, the Shidenkai proved roughly competitive with American fighters. However, Japan produced fewer than 1,500 Shidenkais compared to over 12,000 F-6F Hellcats and over 12,000 F-4U Corsairs. Industrial capacity constraints, strategic bombing, and material shortages prevented Japan from deploying advanced designs in sufficient quantities to affect the war's outcome. By the time Japan could produce aircraft incorporating lessons about protection and structural strength, American numerical and technological superiority had become overwhelming. This represents perhaps the greatest tragedy underlying the paper airplane characterization. Japanese engineers understood the limitations of their earlier designs and developed solutions, but industrial and strategic realities prevented implementation at scale. The perception of Japanese aircraft as inherently inferior obscured the fact that Japanese engineering could produce competitive designs when circumstances permitted. Conclusion: myth, reality, and historical understanding. The characterization of Japanese aircraft as made of paper represents a complex interplay of truth, oversimplification, and wartime propaganda. Japanese aircraft were not literally constructed from paper, nor were they shoddily built in the early war period. Rather, they reflected sophisticated engineering decisions that prioritized performance and offensive capability over survivability and protection. These design choices proved effective in 1941 to 1942 when Japanese pilots possessed superior training and when the strategic situation emphasized offensive operations. However, as the Pacific War evolved into an attritional struggle where pilot survival and aircraft durability became crucial, Japanese design philosophy proved increasingly disadvantageous. American aircraft, designed with greater structural strength, armor protection, and self-sealing fuel tanks, enabled higher pilot survival rates and better sustained operations. The discovery that Japanese aircraft were vulnerable did not occur in a single dramatic battle, but emerged through accumulated combat experience, tactical innovation, and the introduction of superior American aircraft. American pilots learned to exploit Japanese aircraft vulnerabilities through tactics that emphasize their own aircraft strengths: structural durability, diving speed, and concentrated firepower. As the war progressed, Japanese aircraft quality genuinely deteriorated due to industrial disruption, material shortages, and collapsed manufacturing standards. By 1945, some Japanese aircraft genuinely approached the paper airplane characterization through poor construction, inferior materials, and desperate improvisation. However, this late-war deterioration differed fundamentally from the sophisticated engineering of early war Japanese aircraft. Understanding this history requires moving beyond simplistic narratives of technological superiority and inferiority. Japanese and American aircraft represented different engineering solutions to different strategic problems, developed within different industrial and economic contexts. The American approach proved superior under the specific circumstances of the Pacific War, a prolonged attritional struggle where industrial capacity and pilot survivability determined outcomes. The paper airplane myth persists because it contains elements of truth while supporting comfortable narratives about American technological superiority. A more nuanced understanding recognizes that Japanese engineers made rational decisions based on their circumstances, developed sophisticated aircraft within significant constraints, and produced innovations that influenced post-war aviation development. Their design's ultimate failure reflected strategic and industrial realities rather than inherent engineering incompetence. This historical episode offers broader lessons about technology assessment and cultural perception. Engineering solutions cannot be evaluated in isolation from strategic context, industrial capacity, and operational requirements. What appears as a flaw in one context may represent an appropriate trade-off in another. The paper airplane characterization, while serving wartime purposes, obscured the complexity of Japanese aviation engineering and perpetuated simplistic narratives that hinder historical understanding. Modern analysis must distinguish between deliberate design choices, early war Japanese aircraft, the consequences of overwhelming enemy material superiority, mid-war period, and genuine industrial collapse, late war period. Only by maintaining these distinctions can we achieve accurate historical understanding of Japanese aviation technology and the Pacific Air War's evolution. The story is not one of paper airplanes confronting superior American engineering, but rather of sophisticated Japanese designs making rational trade-offs that proved unsustainable against American material supremacy and tactical adaptation.